So we've defined this term called work. It's given a formula of force times displacement times the cosine of theta, and it's measured in a unit called joules. And the joule is the same as the Newton meter, but this work term is measured in joules. So then we have these formulas for kinetic energy, for gravitational potential energy, and for elastic potential energy, and they're all also measured in joules, and they've been designed, those formulas have been designed in such a way that things work out nicely. We have all these situations where we see that this conservation of energy thing, or in other words, conservation of joules, is taking place. So I want to see if we can start with this work formula and try to see why the kinetic energy formula is the way it is, and why the gravitational potential energy equals mgh, and why does the spring's potential energy equals to half kx squared. So focus on kinetic energy to start with. That's the energy due to the motion of an object. And so let's just say we have an object that's totally at rest. It's totally at rest. So its speed is 0, and its kinetic energy would therefore be 0. Like 0 makes sense. If kinetic energy is supposed to be the energy due to it moving, and it's not moving, then it makes sense it would be 0 joules. And if this object is at rest and it's staying at rest, that must mean that the forces are all balanced. There could be 2 forces that are opposite to each other in balancing. There could be 10 forces that are somehow perfectly balancing each other, so this stays at rest, but regardless, the forces are totally balanced. Now we're going to give this some kinetic energy, and that means we got to get it moving. And how are we going to get something moving? Well, we're going to unbalance these forces. So whatever forces are there already, they add up to 0. Well, now let's introduce this one extra force to unbalance all these forces. So this force is going to end up being the net force, and that's going to cause this object to move. It's going to cause this object to accelerate. And we'll apply this net force for a while. And this object should accelerate, this object should speed up. And this will be moment 2. So we have moment 1 here, we have moment 2 here. And now it's got some kind of a speed. It should be faster now. I'm going to call V2. I'm just going to call it V for whatever speed it has. And it should have some kind of kinetic energy. And it's going to be in joules. It's not going to be 0 though. Okay, so it's going to have some kind of joules now that we're going to call kinetic energy. And let's just say that we push this for a displacement of d. And that's how long we applied that net force for. So what's a good formula that we can fill in the blank there, and that's going to give us the kinetic energy of the box at moment 2 now? Well, it's got some kind of a joules now. So where did these joules come from? It had 0 joules of kinetic energy, but now it's got some kind of joules of kinetic energy. Where did these joules come from? Well, it came from the force. It came from the force. Now, force is measured in newtons, so it's not a direct translation from newtons to joules. However, we know that if we do force times displacement, then we can get Newton meters, which is the same as joules. So a good formula for kinetic energy may actually just be the work done by the force. The work done by the force on the box gave this box kinetic energy. And that is force times displacement times cosine theta. Now, cosine of theta, it's going to be cosine of 0 degrees because the force is in the same direction as the displacement. So that just equals to 1. Now I'm going to do a little bit of algebra work here. So the net force due to Newton's second law is mass times acceleration, and then times displacement. And the acceleration is going to be constant as long as the net force remains constant. So since the acceleration is constant, we can apply some big 5 formulas. And one of the big 5 formulas is as follows. So this big 5 formula, if this box starts at rest, v1 is 0, and the acceleration can now be rearranged to v2 squared over 2 displacement. And what happens if I sub this expression, I'll call it star. What happens if I sub expression star in for the acceleration? Then the expression becomes m times v2 squared over the magnitude, we're doing magnitudes here, over 2 times displacement, and then times the displacement. So in this expression, the displacements cancel out, and we are actually left with half mv squared. Remember, I let v2 equal to v. So this is how much work the net force did on the box. And that is why we use that formula for our kinetic energy. And it's going to be measured in joules. All right, so let's do gravitational potential energy now. So let's have a similar situation, but now we need some kind of a ground, and we'll have a block on a ground. And we'll start it just there. Need some kind of a reference height, so we'll make the ground a reference height. And we're going to try to figure out why mgh turns out to be a good formula to use for gravitational potential energy. Okay, so we're going to pick up this box. And we're going to have to apply some kind of a force. Right now there's gravity and normal that are balanced out. But we've got to pick it up. We've got to apply some kind of applied force. And let's just say we pick it up over a height, or a displacement of h. So now the box is up here. So on the ground, it'll have no gravitational potential energy because we kind of set the reference height to be there. And now when we lift it up, now we say, okay, now it should have some kind of gravitational potential energy. So it's going to have some joules stored up. If I were to let this box go, it would fall down. So it's got some stored up joules here. And where did those joules come from? Well, those joules came from the applied force. Now, we could, if we try to do what we did last time with kinetic energy, and we'll say, okay, well, it got this joules from the work done by the applied force. The work done by the applied force is the magnitude of the applied force times the displacement, which in this case it's the height, times cosine of 0. I'm just not even going to write down cosine of 0 because it's equal to 1. And you think, okay, so there's a good formula for, that should be how many joules it has now of gravitational potential energy. And if we say that the displacement is h, the height that we lifted by, then we can see kind of where the h comes from in the formula of mgh for gravitational potential energy. But why should it be mg? Why should the applied force be mg? So the problem we run into here is that this applied force can be all sorts of forces. Somebody could apply a really strong applied force and lift that box up really quick, get it up there really fast. Or someone can take their sweet time, have a lower applied force, and make this box gradually, slowly lift up and still get it to the same height. And those would be two different applied forces. And those would be two different number of joules. But we don't want that to happen. We don't want it to be 10 joules sometimes and 20 joules the other time. We want it to be a consistent, same number of joules every single time. So the way that we actually, or physicists have actually defined these formulas for potential energies is they use this this rule. This is a rule. Where the change in potential energy should equal the negative of the work done by gravity. Or, well, not that, well, in this case it's gravity, but in general, it's the conservative force, whatever conservative force we're trying to find the formula for its potential energy. So using this kind of criteria, we can come up with an appropriate formula for gravitational potential energy. So based on this criteria, we should have the change in potential energy, or delta U, should equal to the negative of the work done by the conservative force. In this case, the conservative force is gravity. So this is the setup they use to define this formula for potential energy, and it's going to lead to mgh. So if we change delta U to U2 minus U1, and we have the negative of the work done by gravity. Okay, so just copy down the negative sign. Now the work done by gravity would be the force of gravity times the displacement, which is going to be the height, times cosine of theta. So what's theta here? We're not talking about applied force anymore. We're talking about the work done by gravity. The force of gravity is down. The force of gravity is down, while this box is actually being lifted up. So that force of gravity is actually in the exact opposite direction of the displacement of this box. So it does turn out to be 180 degrees, which is equal to negative, cosine of that is equal to -1. So it started on the ground, the reference height. So U1 is 0. So the gravitational potential energy at my position above the ground will equal, so the negative and the cos 180, that's basically two negatives. It makes a positive. Fg is mg, and the displacement is equal to the height that we lifted the thing. And this is why mgh ends up being the formula they use, or we use, for the gravitational potential energy of an object. It is heavily reliant on this criteria here. And we're going to do the same again was written on the previous slide. For elastic potential energy now, this will be the last one. So we kind of just learned this. So elastic potential energy, it's a conservative force. Every conservative force has a potential energy defined for it. And the criteria for defining this potential energy, I'll write it again here. The change in potential energy should equal the negative of the work done by the conservative force. Actually, I'm going to explain that a little bit. No, I'll keep going here. Okay, so this time we'll have a situation with a spring. And we'll have a string attached to a block, and we'll make this frictionless because we don't want to deal with that. And this will be just this will be the start position, the rest position. So the spring is not stretched at all at the start position, which means it doesn't have any potential energy stored up. But then we're going to pull it, and we'll pull it a certain displacement. Well, it'll be x. Okay, we'll pull it by some amount that we'll call x. It's going to end up over here. So the spring is going to be stretched now. And now that the spring is stretched, it's going to have some kind of joules. How many joules should it have? Well, we're going to follow this rule here. The change in potential energy should equal to the negative of the work done by the conservative force. So the change in potential energy should equal to the negative of the work done by the spring force, this S for spring force. So why is it negative? So here's the thing. This force I had to pull the block with, the force I pulled the block with it was going against the spring. It was going against the spring. So the spring is actually doing negative work when I pull this block. But the applied force is doing positive work. And the applied force is it's storing up the joules in the spring. That's not a really good explanation, but that's the best I can do for now as to why the negative sign is there. To get the box to move from A to B, how did we make that happen? We had to go against the spring. How much work did the applied force have to do? Well, it had to at least counteract the negative work that the spring did on it. So we stick a negative sign there. The spring did negative work, but we want our potential energy to be a positive value. So we have a negative sign stuck there in front, so that two negatives make a positive. Okay. Yeah, that's not a very good explanation, but we'll just go on from here. So delta U would be U2 minus U1, where I started this situation off with no stretch in the spring. And this will be the negative of the work done by the spring. So negative of the force of the spring times the displacement times cosine of theta. Actually, I'm going to do something else. Just leave it for now. The work done by the spring. The thing about a spring is that the force varies. The more you pull it, the stronger the force is, and it makes a linear function. So the work done by the spring is actually calculated by this area here. It's calculated by that area here, where on the x value, well, this is x. This is how much we pulled it by. And the force starts at 0 newtons, and the force gets stronger as you pull it more, up to, so how much force is at the very end there? Well, that would be k times x, actually. K times x, that's Hooke's law. So the work done by the spring is equal to the area of the graph. It's going to be negative since it's below the axis there. So it's the area of a triangle, which is half base. The base is x, and the height is kx. Well, negative kx, so this is negative. So that's equal to negative half kx squared. And that should look familiar now. So the potential energy is now negative of the negative of half kx squared. Negatives, two negatives make a positive. And this is where our formula comes from for the potential energy of a spring.